Okay, what we're going to do here is we're going to finish off our worksheet on integration by parts. It's on my website, mathsresource.com. You can probably read it in the description. Just again, recap, integration by parts. This is the formula here. So what we're doing here is we're trying to integrate a complex expression, and what we're going to do is construct it in the form u dv, and to solve that, the formula is uv minus the integral of v du, with the idea that the integral of v du being much more easy to solve than u dv. Now, the important rule here is the Lipit rule, which is worth mentioning again and again and again. This is a rule for determining which of the... sometimes you have several choices of expression, and you have to determine which one should be u. So a very useful rule here is the Lipit rule. L-I-P-E-T, and essentially if you have logarithms or something like that, log of x, let's say, that would be the best choice to have that as u. Inverse expressions, for example, cos minus 1 of x or something like that, or sine minus 1 of x, sine to the minus 1 of x. Polynomials, for example, x, x squared, x cubed, so on. Those would be polynomials. They'd be the next best choice. E to the x, exponentials, e to the x, e to the 2x, e to the 4x, that sort of thing. That would be the next best choice. And lastly, you would have things like trigonometric functions, sine x, or what we're going to look at in this one is hyperbolic functions, such as sine x and cos x. Okay, so we have two examples in this one, and the first one is x sine x dx. Okay, so the Lipit rule states that this is a trigonometric function t, this is a polynomial p, so necessarily what we're going to do here is we're going to u equal to x and dv equal to sine of x dx. Okay, so we're breaking it up like that. Okay. So how do we solve this? Well, first off, if you go back to our formula there, uv minus v du, we need to find v and du. So first off, du over dx is the derivative of x, that's equal to 1. Therefore, we can say du is equal to dx. Okay, now we have du in terms of x. V is what we also need, and this is the integral of d of v. Okay, and that is the integral of sine x dx. Okay, now the integral of sine x dx is cos of x. Okay, okay. Just as a remark, I'm just going to write this here at the bottom. Both the integral and derivative, what you get when you differentiate something, of sine x is cos x, and vice versa. Derivative and integral of cos x is sine x. It's sort of why these hyperbolic functions are fairly interesting. So, if you were to get the derivative of that again, you would get sine x, or the integral of that. Okay, so we have u, so this is what we're working with, uv minus v du. So the what we're dealing with here is u is equal to x, v is equal to cos of x, and integral of v, that's cos of x, times du, and that's equal to dx. Okay, so as we sort of said before, the integral and derivative of sine is equal to cos. Likewise, derivative and integral of cos is equal to sine. So the answer to this one is cos of x minus sine of x plus c. So that's the answer there. That is the integral that we're looking for. X cos x minus sine x plus c. Okay. Just as a sort of quick remark, with the indefinite integrals, never ever ever forget to put in that plus c. Okay. One more and we'll wrap it up. So this one here is something similar. E to the x cosh of x dx. Okay. So, Lipit rule. This is an exponential. This is a trigonometric. So we're doing something very similar here. U is... Oh, this is going to be a long one, actually. Sorry. I'm going to go through this part of this. So just brace yourself. This is a long one. So U is equal to e to the x. Okay. And there's a long one to this, actually, but there's a sort of quick way at the end. Du dx is equal to e to the x. Okay. Now, v or dv is equal to cosh of x, and v is the integral of that, the integral of cosh of x, and that's equal to sine of x. Okay. So putting that together, we get u times v minus the integral of v du. Okay. Now I'm going to sort of state integral here. I'm going to be very clear. I is for the integral that we're trying to resolve. Okay. So I equals uv minus v du. Okay. So integral equals... I didn't use this the last time, but I'm gonna. It's more necessary this time. E to the x sine of x minus integral of cosh x and du, sorry, I should have done this here, is e to the x dx. So what we have here is e to the x dx. Okay. So, working that out, e to the x times sine of x minus this expression here. Let's write it out. E to the x cosh of x dx. And you're thinking, did I see that somewhere before? Yes, you did. This is why I use that integral. So this is the integral here at the start. And this is when it's in the form u dv. Okay, so just think about that. That's the integral, the original integral. Sorry, that's e to the x there. So, what's this about, so? So let's just write this out. I equals e to the x sine of x. What do we do? So, well, it's minus I. And I'm thinking, that might be we might be onto something here. We got I equals such and such minus I. So, 2I, let's just add I to both sides, equals e to the x sine of x. And divide that by 2, e to the x sine of x over 2. That actually works. So, this is a sort of trick to this one. This is when we come to this second derivative here. Okay? This actually, look out for it. You're thinking, are we back to where we started? And yes, we are. And that actually is good. This is the original integral that we're trying to resolve here. So let's just rephrase it as I, just to make it, just actually to cut down on the notation. It's not absolutely necessary. But you can sort of see I equals e to the x sine of x minus I. And you're thinking, hang on, we can resolve that, because what we need is this here. Okay? Just because we have I equals that minus I isn't really a problem. So, essentially all we have to do is add I to both sides. 2I equals e to the x sine x. Okay? And then divide by 2, and we actually get the integral we're looking for. Okay? So, it looks a bit harder than it is. But this bit here is just keep your wits about you and look for these little tricks. Can you sort of resolve it like that? That actually happens quite a lot in integration by parts. So that's a really nice one there. I'll leave it there anyway.